So we've been talking about the PD diagnostic technologies, and as I said, those are the fundamental, those are the basis of all the applications that we're going to talk about in the following 20 or 30 minutes. So commissioning test is apparently commissioning test is performed after the installation of all the cables and accessories. So it's also called after laying test or acceptance test. And the purpose of the test is to detect the shipping and installation damage in both the cable and the cable accessories. And there are a lot of standards giving standards or guidance to help people to perform the commissioning test. And the most common commissioning test that we do for medium voltage cable system or even for high voltage system is to do the following two tests. One is it's called monitor the withstand test. So first, it's a withstand test, 1 hour withstand test at elevated voltage. If we're talking about medium voltage, normally it's around 1.7 to 2.5 or 3 knot operating voltage. And such elevated voltage will be applied to the cable under test for 1 hour. And during the withstand test, the PD test will be performed and to check whether there's any PD activities. So compared with the conventional withstand test, apparently PD test it's applied during the test. So even if the cable passed the withstand test, that the cable didn't fail during the withstand test, and the PD can still find small defects that will not immediately fail the cable, but will shorten the useful lifetime of the cable very effectively. And the alternative method is the 24-hour choke test. So some customers or some applications we don't have the condition to use external power supply or to apply elevated voltage to the cable system under test. The alternative method is to energize the cable for 24 hours without load. So this is called a soaking period. 24-hour choke test is also a guidance in the I2B standard. And apparently PD test will be performed during and after the soaking period, and to ensure there's no defect or no PD activities within the cable systems. So that's the general two method of doing the PD test, the commissioning test. So the equipment that required for the test, first, of course, we need to have a power supply to energize it, unless we're doing 24-hour choke test. So 24-hour choke test will be more like an online testing that will be covered in the maintenance test. So mainly we're talking about the offline withstand test. So power supply, typically we have 3 power supplies, and I'll go from the bottom to the top. The bottom is a very simple one. The power frequency high voltage power supply works at power frequency, and the size is pretty large. We need to use truck to load it for the test. And also the size is proportional to the length of the cable, and also proportional to the frequency of the power supply. Besides the power frequency high voltage power source, there's also near power frequency resonance tester system, or called RTS. So that system, instead of using a transformer to boost the voltage, it uses the resonance circuit. The power supply has a big inductor, and the cable is a big capacitor. So that's a RC resonance circuit with different resonance frequency. The voltage can be pretty high, and the size of the resonance power supply is also large. It requires, here's some example, requires the signal generator, inductor, and the big insulator to support the testing lead to do the test. And also the frequency of the RTS is not a constant. It depends on the length of the cable, depends on the size of the cable. So normally the frequency changes around 20 to 150 hertz, as I said, depends on the cable condition. And the very low frequency, it's very popular for medium voltage cables. VRF testing power supply, the size is much smaller compared with the power frequency or near power frequency power supply. Here's an example here. This is a 30 kV VLF power unit. The frequency is a 0.1 hertz or 0.01 hertz, and the output waveform is also sinusoidal waveform, similar as the power frequency, but the output frequency is 600 times lower. That's the reason the size of the power supply of VLF is also much lower and lighter than the power frequency power supply. So normally the output current of that VLF unit is in the range of 10 milliamp or 20 milliamp. So if we're talking about a very long cables, it has some challenge. But if we're talking about 2 kilometer, 3 kilometer, or even 5 kilometer cables, it's fine. I think most of the VLF unit can load cables up to 5 to 10 kilometer long. So after we talk about power supplies and the sensors that we normally use, there are 4 types of sensors that we normally use. The most typical sensors are the HFCTs and the coupling capacitors. I'm not going to go to too much of details on that. HFCT, probably you guys all see that, put it on the ground lead, and it can measure the PD-induced current. Sensitivity pretty high, very easy to install. It doesn't have synchronization because when we're talking about phase result pattern, all the measured PD pulse needs to be synced or be presented in the power frequency. So we need to have external source for the synchronization. This is the low frequency current transformer, which is used to capture the 50 or 60 hertz signal during the test. So that will provide a synchronization for the PD signals. So this is the most common sensor that we use, or everyone use for the PD world. Another alternative one is the coupling capacitor. Coupling capacitor also very high sensitivity, optimal sensitivity. Coupling capacitor, normally it includes a capacitive divider. So the coupling capacitor itself can provide a PD channel and a sync channel. So no external sync is required. The challenge of using the coupling capacitor is it needs to access to the cable conductor. So it can only be used in offline test, and it has some operational safety requirement to use that. So in the case that we cannot use these 2 types of sensors, here are the other 2 sensors that we can use. The FMC flexible magnetic coupler. For example, if we're testing a splice and there's no ground wire, how are we going to do that? The FMC is a good choice. We can put it next to the splice, and it will capture the PD-induced current going through the sheath, and it will have similar, a little bit lower sensitivity than HFCT, but since it's very close to the splice, the sensitivity is acceptable. And another similar option as the flexible magnetic coupler is non-galvanic capacitive sensor, like this. Use a hot stick, put it around the splice to take the readings. So these 2, the FMC and the UCAP sensor, are quite similar. Instead, the difference is FMC acquires magnetic signals, current, and the UCAP, it captures the electric signal, the voltage. So those sensors are the sensor families that can handle almost all the applications. And PD instrument, Aquila portable PD testing equipment, we have a couple of choices. We have 3 series. So this is the most common one that can be used in the on-site test. So that one, it's portable unit with battery power. 2 batteries can last up to 12 hours. And it has the Bluetooth and Wi-Fi connection. So this is one example testing in the wind farm joint box. So this equipment is connected to the equipment to the sensors, and the operator connect to the equipment by the Wi-Fi, and it's very flexible, very effective to perform the on-site test. And so the Aquila, it's based on the PD check series. We have another equipment called a PD base. PD base is a more powerful, advanced equipment. In many cases, used in the lab condition. It can be also used in field condition. And the third theory is called Falcon. That's for the monitoring solutions. It has more computing power and the data storage power within the unit. It can do the monitoring and the calculation by itself. So we're going to talk about that later. So the testing procedure, a very simple procedure. First is to set up the power source, make sure the power supply it's connected. And after setting the power supply, we need to install the sensors. If we're using HFCT, it's quite simple. Find the ground lead and put it around. And after we have the power supply set up and the sensor installed, we need to do the sensitivity check to make sure the entire system is working. So this is an example of sensitivity check. We can see we inject a calibration pulse and we can see the reflections from the far end of the cable. We can see the secondary reflections from the far end of the cable as well. So that will ensure that the whole system is functional and also the sensitivity is optimal. It's optimized. And the third part is to apply the voltage and do the PD measurement. And the testing result, as I said, we do not directly give the raw data. We do not just give the PD magnitude or repetition rate or PDIV or PDEV. Instead, we use the traffic light system to indicate whether there's a problem within the system. So this is a decision tree. So it depends on what type of defect we're looking at and what testing voltage we're looking at. Then we give the recommendations: red, green, red, yellow, green. Red apparently means the component needs to be replaced or action needs to be taken. Yellow means there are some activities, but it's not that critical. We need to keep on watching it. And green means everything's fine. Keep on moving. So one case study, I'll go through that quickly. This is a commissioning test for the inland wind farm 35 kV TRXLP cables. The cable length is pretty long. It's over 3,000 feet from junction box to junction box. And we use a VRF power supply to do the test. And the testing voltage, we selected 3 testing voltage. And the highest voltage is not in the range of 2 U0, as it's limited by the cable termination. The cable termination manufacturer has its own spec on the highest voltage that can be applied. And the equipment that we use for this test is the PD base. This is the one that I talked for the lab use. This is a very good equipment for the very low frequency PD test. So this is the sensitivity check. When we do the sensitivity check, we inject a pulse and we see the reflections. Even though the cable is very long, we can still see the reflections. And the injected pulse is very small. You can see we injected 5 picocoulomb pulses into the cable, and we can see the reflections. So that ensures our testing sensitivity is very high. And here is the acquired discharge pattern. There are some activities, and we use the TF map to separate the signals from different sources. And the 2 types of discharge activities or clusters can be distinguished and separated. And we do the analysis on each individual clusters, and that requires the criteria that we talked in the PD detection technology. We need to locate where the sources are, and we need to evaluate if those PD activities are harmful to our system or not. And for this test, the conclusion was both these 2 discharge activities are external to the cable on the test. One is the surface PD, likely coming from the testing lead. One is the external corona PD, maybe from the sharp edge of the coupling capacitor or the power supplies. So the final result is all the tested cables are in good condition, and commissioning, all the cables passed the commissioning test.